morning, very good. Let's see how it goes. This is the first lecture that I am giving on artificial neural networks. So let's see. Before, I have given quite a number of lectures on neuroscience and biological neural networks. Yeah, artificial ones. So let's see. Let's see. So my name is Alejo Nevado. Who does an amazing Windows 3. So let's see. So my name is Alejo Nevado. I work in the Big Data Institute and in the Department of Psychiatry, mainly on the applications of artificial neural networks to health data and to genomics. And in health data, we work mainly with natural language processing, with extracting information from the text held in hospitals and electronic health records. For you to know a little bit where am I coming from, and then that might help you see if I am missing some pieces of information or talking too much about others. So I have my background in computer science, like all of you, or most of you, and also in physics. Then later I did a PhD on computational neuroscience and biological neural networks. Then I was around Cambridge, Oxford, and so on, and I have ended up here. And since the beginning, I was very, very interested on neural networks during my master, like most of you. But back then, neural networks were not cool yet, so everybody was telling me not to bother about them because they were obsolete and blah, blah, blah. So I went into biological neural networks to try to find what they have so special that we are not able to mimic in artificial neural networks. But then at some point, I started hearing of neural networks being amazing again, so I moved back to my favorite field, and now I am very happy because they are working amazingly well. And yeah, and the lectures are going to be about how we can use them in natural language processing. So I have an amazing accent, so if you don't understand anything, which will be likely because of my accent, then simply interrupt me and I can explain a bit better. Okay, so how is the course structured? So I think that if we try to make sense of how different books and courses try to structure the material, not only in NLP but across fields, there are many books that present a field in a method-oriented manner, so every chapter or every lecture is about a specific method, and then when they are presenting the method, they talk about which problems they solve very well and which ones not. This course, however, is that other type, which you can also find out with a number of books and other courses, that rather than explaining one method after another, we explain what were the main questions of the field, present it a bit historically as well, because historically they got also sorted in levels of difficulty. And in that process, we explain what were the first very good methods, or when was the first time that recent methods started solving that problem. And the advantage, so this other method-oriented manner is better for Wikipedia and for consulting stuff once you know what's going on. I think this other method is much better when you have a first introduction to a new field, because it helps you know a little bit how we have been progressing from one method after another, such that it helps you think about how to solve the problems that are still not solved, which I think is better also not only for introductory courses like this one, but this is not really an introductory, but not only for courses like this one, but also to focus you more on research. And okay, the whole structure of the course. So I have tried to follow a bit the slides of the previous year, just in case there were some very, very hardworking students that could not wait for this amazing course, and then they were already having a look at the slides that Thomas had from previous year. But I have tried to give more structure to the course and so on. So the first few slides are going to be about the introduction, what is NLP, and blah, blah, blah. Then later we go to the first problem that natural language processing was trying to solve for many, many years, which is how do you represent the meaning of a word. So if you, rather than going for the big problem of trying to get all the meaning of full text and conversations, you start from the easier part. How do you get the meaning of words? Then later we go to a very typical problem that is name entity recognition. How do you recognize the general classification of specific words within a text, and this is a type of task that is extremely useful in industry and so on. Then later, in following lectures, we will start talking about more interesting modern applications or all problems that have suddenly, that are starting to be cracked now, like language modeling. How do you model the probability of language and how that allows you to actually get like an embedding, but not only of a word, but of a full piece of text, and how that then can be used for kind of everything. And then later machine translation and so on. Later on we have more lectures, but I am not going to talk about the whole structure of the whole thing because those are a few weeks away. And then what we are going to talk in this first lecture is simply the introduction, which is going to be quite short. Then later, how do we represent words? And this lecture, they set up the lecture of this course with 2 lectures coming at a time. So we are going to have here 2 hours, so it is a bit long. But then we will be able to talk everything about how words are represented. Okay, and the next one, so what is NLP? Many of you will know already what NLP is about, yes, but there will be some that are coming from physics or mathematics and so on, so they will be so familiar. So the definition of NLP, there are like all AI approaches, there are many different definitions, all of them are more or less intersecting, but the topic is so general that it is difficult to define it successfully. So the one we can use is simply how we can make algorithms and methods that are able to process text. And you say, oh, process text, that's very boring, but word processor already does that. But it is not processing on that limited sense of the word, but processing in the broader sense of the word. So also processing in the way that we humans represent words. Or represent words, or are able to deal with language, like question answering. How are you able to represent, to search stuff in PubMed or in Google? And it is one of these problems that looks very easy at the beginning, but later they are tremendously hard. And that difference between expectations and reality is what has generated a number of winters in AI, quite dramatic winters, and hopefully they won't happen ever, but simply a word of caution there. Then the challenges, the typical challenges that it solves, I have mentioned them already. Text classification, so given a piece of text, what is the text about? So is it a legal text? Is it a text about animals or whatever? And that seems easy, but it wasn't that easy really. It was one of the first tasks that got solved, but not much. Then machine translation, that's a much harder one. That the methods nowadays, they are not human level performance, but are getting quite better. Language modeling, question answering, conference resolution, I will define that later when the lecture arrives and so on. And then the applications that this has a very good number of applications. So the more modern ones that are coming to the news are things like digital assistants that are able to deal with a few topics, but text classification, for instance, it is also tremendously important. The ones that you might be too young to remember the times in the 90s when search engines were really awful. You will search for, when you wanted to search something on the internet, of the top 50 websites, only perhaps 3 were about the topic you wanted to see about. And that was because text classification, website classification was not well solved then. But nowadays, when you search something in Google, it gets, you get what you are looking for in the first intros. I mean, I guess that all of you are now programming by using consulting Stack Overflow and so on. That was impossible before. It will take you forever to learn a new language because internet couldn't help. Then automatic translation. So I will talk later about the different applications. I have some screenshots and so on. Okay, and what I was always talking about before, why is it so hard? So in artificial intelligence, most of the problems look relatively simple because we humans are extremely good at solving part of artificial intelligence. But in reality, it is a very hard problem. So to show to you a little bit how hard it is. So in the case of language, for instance, language is often very ambiguous. So a given word has several synonyms, several definitions, and it is not predefined how which one every piece of text is using. Then the grammar and the syntax is quite complex, and very often we simply skip it, especially when we are talking. When we are writing, we are a little bit better, not in Twitter, but in other places. And then humans use a huge amount of previous knowledge that is not easy to code in the computer. So an example, a bit exotic example that I came up with is this sentence, like, Tesla explosions concern Mr. Musk. And some of you, the ones that are keen to follow the history of Tesla, the company, and SpaceX and so on, might know what this sentence is talking about. It is talking about the fact that batteries in the Tesla cars tend to overheat and catch fire, and then the car blows up. So then someone that is aware about that prior knowledge will know what this sentence means. It means that that fault in the Tesla cars is concerning Elon Musk, the head of the CEO of Tesla. But then you start think how a person from the 90s will understand this sentence. I mean, Tesla, what is Tesla? Is it this guy, the guy, the famous electrician from 100 years ago? Is it the unit of measurement of magnetic fields? But no, it is actually this other thing. It is these cars. And what is Musk? Is it these funny animals with big teeth, or is it this guy? I mean, this guy was unknown in the 90s. So for humans, it is quite easy to disambiguate all that stuff. But for a machine, tell me, how did you put that into a machine? There has been a lot of attempts from the 50s, but it has only been with neural networks that we start getting machines to get a bit of the meaning of this word. And what else did I write here? Yeah, that was everything. So this was a bit of the problems. And now with neural networks, they seem very easy. But when I was doing my degree, that was just before neural networks became a thing. There were so many approaches to try to solve this, and hardly any worked. Okay, why neural networks? So the way neural networks work very well is because before any other technique had a lot of problems that were arising over and over again. So usually what you will do is to pre-design manually features that were able to get like corners or pieces of the information of the problem in a way in which, in a multidimensional space, it will make a nice representation that can be divided by a linear classifier, a super vector machine, or something. So an example would be, imagine that you want to classify pictures on whether they are from animals or they are from cars. Then a manually designed picture there could be to count how much green or how much value there is in the green channel of the image, because most animals, they are jumping around often in the jungle or the countryside. So then if you see a picture with many green pixels, then possibly it is from an animal. And then in cars, you say, well, the ones that have a mixture of all sorts of colors and so on. But then you see how easily that feature breaks down and stops being useful, because what if your animals are coming from the Arctic? Then everything is white. Or what if your animal is coming from the desert? Or what if your cars are coming, it is a jeep running around in the forest or anything? It doesn't get you a good classification record. You will combine it with other features, but even if you combine it with many, you will hardly get 90. And what if suddenly you change the topic, and rather than classifying animals and cars, you want to classify planes and cars? Then you have to change your features to counting blue pixels or something. And then learn features rather than manually. So those manually designed features are quite difficult. You have to change them if the problem changes. But learn features, so features that a neural network or other method automatically learns from data. Not only neural networks learn from data, also super vector machines were very good, for instance. If you, rather than designing your features, you learn them automatically, then when you change your topic, you simply need to collect a lot of more data, and then you train your algorithm again, and it should work more or less the same, depending on how complex the underlying space is. Other thing of deep neural networks is that they are extremely flexible. So, for instance, imagine again the example of counting the pixels in an image. So you can do that in an image, but what if suddenly you want to analyze audio? So you don't have pixels anymore, so you cannot count stuff. But in neural networks, they are so flexible that you can apply the same architecture both to an image and to audio. For instance, a recent architecture that is working very well is the transformer architecture. You can apply the transformer architecture surprisingly to both images and audio and text to anything. And with attention, other modern technique also to anything, or LSTMs. So that's extremely surprising. And then also deep learning, or neural networks can learn in an unsupervised manner. That's something that traditional techniques like support vector machines and so on are not easy to adapt. So that means that you don't need to annotate a crazy amount of data. And the other one, well, why did I write the last one? Well, anyway, you can also do supervised learning. I guess that was what I was thinking back then. Okay, and why neural networks are so famous now when before people was very discouraging? I mean, there was like a veto in neural networks before, which was very frustrating. You had to hide that your paper was about a neural network, or it wouldn't get published. Which is a word of warning, because we might be doing now the same, but the other way around. You need to have neural networks in your paper, or it won't get published, which is quite bad. So why? Well, the thing is that there were three, usually, depending on the person you ask, it will change the story, but usually people tend to mention, and I agree, these three developments. First, data became much better and much larger, hardware as well and software as well. Data, so I remember in the 90s, so the data sets that you will have for classifying pictures of cars and animals, you will need to get a lot of pictures of that stuff, and then where do you get them? This is before the internet and before anything. You will have to take normal pictures, scan them, and scanners were not that common, and then put them in a computer that perhaps had a memory of 32 kilobytes, which yeah, they were counting kilobytes. And you had to then hire a person to annotate them manually. So you will go to a couple of hundreds of data points, which was quite terrible. So only the simpler techniques, like linear classifiers, will be able to do something on that. Any other more complex technique, like a neural network, will drastically overfit the data. Then hardware. Well, yeah, what I said about the 32 kilobytes, those were computers in the 80s and so on. So it has only been more recently with the Moore's law, although we don't seem to be following anymore, but it is only through the Moore's law that we have been getting faster and faster computers with more memory, more this, more everything. And now the bigger jump that we have suddenly given, thanks to the industry, thanks to the fact that all of us are playing a lot of video games and we pay a lot for playing like Call of Duty and so on, then that has pushed the industry to develop even better hardware for high throughput, because CPUs are designed to deliver computations very quickly one after another, but GPUs are much better, not only for video games, but also for science and neural networks, because what they try to do is to compute as much as possible in the long term, not compute as much as possible in the short term, like a CPU. And the jump to the GPUs has allowed us to, so when you compare a CPU to a GPU, you get an increase in long-term performance of 2 orders of magnitude, which we will have needed like 2 decades to get that in a CPU. So that has allowed us to jump a couple of decades in the capability of a computer. And then software, this is the more interesting part. So also the neural networks, although many people might disregard sometimes, if you don't like neural networks, they will say that software hasn't advanced, that everything was invited when I was a professor in the 90s. Well, not really. The thing is that now, thanks as well to data and hardware, people have been able to explore much more the neural network techniques and evaluate much better what little improvements you get with neural algorithms. So now, for instance, before in the neural networks that are used a lot in language, before people will work mainly with recursive neural networks. But because the data was too small to realize that LSTM's newer architecture was actually much better than recursive neural networks. So it was difficult to demonstrate that LSTMs were better. But now if you apply LSTM, thanks to the fact that you have GPUs and you can train them, and thanks to the fact that you have a lot of data such that your architecture doesn't overfit that much, then you can demonstrate very easily that LSTM were almost everywhere much better than recursive neural networks. And the same with all other applications. Now we have, rather than stochastic gradient descent, which was the simple way of doing backpropagation, that was the standard one before, now we have other more cool techniques like ADAM and so on, and not only in learning but also in architecture, in how to augment the data, and each one of those little improvements increase a little bit the performance, like a couple percent. But if you get like 10 different little improvements and put them together, and each improvement makes a plus 2%, you have plus 20%, which is really crazy. And yeah, that's it. So these three things has allowed us to, has allowed neural networks to suddenly become that good. I just realized that I haven't clicked this button as the IT guy was telling me. Okay, so maybe the audio at the beginning of the lecture is going to be a bit bad, but now it will be awesome. And again, why neural networks? I guess I have been talking this already before. Okay, but this is more about natural language processing. Yeah, so I was talking about the previous, that LSTM, now it is easy to demonstrate that they tend to work better. Other good improvement has been embeddings. So before, as I am going to explain later, there was a lot of difficulty on how to represent individual words, but embeddings are very good doing that. Then end-to-end learning is also quite good, which is rather than deciding manually all the different features and little steps of a very complex algorithm, you simply put a neural network end-to-end from the beginning, from the input to the output, and if you have a lot of data, it tends to work surprisingly well. Other software improvements, well, I mentioned them before already, attention, transformer, better libraries, that has been extremely useful. I mean, when I was doing my master, I had to create my own mini library for neural networks in C++, which is the most painful thing you can think in computer science about. But now you use PyTorch and so on, and you can download data sets like in one command line. You can train with all the sort of modern algorithms very easily. You progress way faster. And other very important thing that I didn't mention before is industry, because before, and I have seen, and I see this now, because before traditionally I was working only in academia, but now I also work in a startup, and there you realize very quickly how much more efficient a startup, an industry environment is. And it is mainly because they have like 2 orders of magnitude, if you are Google, 2 orders of magnitude more funds. So while in our NLP groups, me and my collaborators in academia, we might get enough funds after a lot of struggle to have 5 people or so. In a company, you have 50. And you are able to advance much faster, not only because of the incremental improvement of having more people, but also because you can specialize them. So that has had the fact that now the AI algorithms are good enough to have an impact in industry, has attracted the attention of industry. They are putting a lot of money, and then that's making the progress way faster. So okay, how in all times, or not so all times, how was people trying to represent words? So the obvious way in which people was trying to do it was to have, imagine that in English we have 150,000 words. Well, in reality we have many more, but imagine that we stop at 150,000. Then the way people was working before was to have like a vector of 150,000 dimensions, and then the vectors will be only 0 and 1s, because you could represent that easily in a Boolean vector in computers with 32 kilobytes of RAM. And yeah, every word has simply a different dimension as 1 and all the other dimensions as 0. So when my teacher of AI was telling me that this was the standard in the early 2000s, I thought she was joking, because I thought, but this is not going to work. This is quite terrible. And yeah, it is quite terrible. So because if you see the distance between the word dog and Labrador, a breed of dog, is as wide, no matter how you measure, as the distance between dog and car, which doesn't make much sense. And also it has many problems. Besides that, well, let's see. Yeah, well, I will skip the problems. I think they are more or less obvious. So how do you put this in a computer? Then all the words have the same distance from each other. Then if you represent a piece of text on this stuff, the data is extremely sparse and so on. So then there were a number of attempts to try to solve this problem. One that was used for quite a while, and that I have used myself as well, was the synsets, or the WordNet. This was an effort where they were trying to create groups of words that represent the same. So now it is coded in some nice libraries, in Python, in C, I think as well, in Java, and then you can query this API to get all the synonyms of whatever word, to get all the words that have a more general meaning of any other word, all the words that have a more specific meaning, and this sounds very well. But this is a very good example of the problem of manually designing features that I was talking about. So the way they will create all these groups of synonyms was by hiring a lot of people that will go through dictionaries to create all these combinations. But now imagine if in English we have 150,000 words, more or less, how many combinations of those many words do you have? So you need to go to these Newtonian binomial numbers, I think they were called, and you get a crazy number. So it is extremely difficult to do it well. And if you use synset, you will realize all the problems that it has. So for very common words like cat and so on, it works very well. But if you go to a very difficult word like cerebellum, it might not even be in the synset. But it ameliorates the problem a little bit, because then rather than having, for instance, a one-hot vector representation of 150,000 dimensions to represent every word, you can, if you compress or simplify your language to, for instance, 10,000 groups of synonyms, then you could represent your words with a one-hot vector of 10,000 dimensions, which is a good improvement. So, but the thing that really started to work much better was the use of embeddings. So the main core idea of embeddings is that, well, it is like two ideas. First, rather than representing things in a very sparse vectors, sparse means that the vectors, if you represent them in space, they are spread all around the n-dimensional space. So rather than using those one-hot sparse dimensions of a lot of dimensions, vectors of a lot of dimensions, why don't we use dense vectors that only have a couple of hundred dimensions, and where the different words are different vectors, different points in that 100-dimensional space, and they are more close to each other, forming a nice cloud where the shape of the cloud has certain properties and so on. But then how do you create those vectors? So you can create those vectors, it turns out, by using a property that linguists have been discussing about for quite long, a property of language, which is that it seems, or many linguists argue, that the meaning of words actually comes from the context in which the words tend to appear. And here I have tried to handcraft an example that tries to portray, to show this case. So imagine the words dog and Labrador. So dog is a dog, and Labrador is a breed of dog. If you start looking at examples, this is very idealized, but if rather than 6 sentences you have 6,000 or 60,000, it will become more apparent. So if you look at the words that also appear in a window of ±3 words, you will realize that the same words, the same types of words tend to appear in the neighborhoods for both the typical neighborhood of dog and the typical neighborhood of Labrador. I use the examples fur, park, and barks. It seems to be, so usually those words appear always around for those two Labradors, for those two words. So how can we use that feature? So then this is telling us, okay, if two words tend to have the same context or similar context, then they must mean something more or less similar. So then this might allow us to create like the scene set example that we were talking about before, finding which words are actually synonyms, but we can do it automatically. We simply feed a lot of unannotated data, all of Wikipedia, to some algorithms, and the algorithm counts or realizes on some way which are the neighboring words of each word. So how do we do it? Well, I have said it already a little bit. So first we get a very large corpus, which is many texts. For instance, all of Wikipedia. Other typical data set is all of the Wall Street Journal articles of the 80s and 90s. Other one is all the text generated in the European Union Parliament, because they like typing everything down because they are very tidy, and that's an amazing data set for us. Then we represent every word with a dense vector. So a dense vector in Rn space, because you have n whatever dimensions, 200 for instance, is a typical number. A dense dimension means that rather than being many of its values 0, and only a few or one of them being different than 0, like in the one-hot representation, rather than that we do the opposite. We allow or we foster that most of the dimensions in that vector, we foster them to be different than 0. And the other thing is then you have a model or an algorithm that does stuff with that vectors and corpus. What the algorithm tries to do is to predict what is the probability of a central word being whatever, a central word being, for instance, dog, given all the words in the context. So the words that are, all the words that tend to appear 3 positions before or 3 positions later. And then an algorithm, once we have this, how do we train this model, whatever the algorithm is, not necessarily a neural network, how do we train it for it to capture this probability? So you go through different steps. This is a way of doing it. You go through every possible central word in the corpus, which could be everything, and then modify the neural network or the algorithm a little bit for it to be able to capture a bit better this probability than it was capturing it before. And then you repeat these 2 steps over and over again, many times, such that you little by little approach to the real probability representation. And this is a typical step done in numerical analysis. For instance, if you look at finite methods analysis, they can approach the value of a complex differential equation that way. Okay, and what do we get at the end when we apply this? We get something like that, and this is what I mean by a dense space. So if we get the 200 dimensional, well, first, we will get that every word will have a corresponding vector where most of the values are different than 0, and then the meaning of the word is embedded on, or it is encoded on the values of those dimensions. And when you reduce the dimensionality to 2 dimensions or 3, simply because we humans, our visual cortex is not able to process more than 3 dimensions, which is quite a pity. But if you reduce the dimensionality to 2, with an algorithm that tries to preserve as well as possible the distances between the different words, such that the distances in 2D are as close as possible to the real distances in 200 dimensional space, you see something like this. So you start seeing that being and being, which being kind of the same, but they have a different tense, are close by. Then all the other words that also mean the verb to be are there. The word to have is also there. Another very typical verb that in English is used a lot, and it is also a auxiliary verb, so it makes a lot of sense. Then become and continue, so this is something expressing that something that changes with time or in a process, which makes a lot of sense. Need and help, they are also very related. So you start seeing relationships like this, which is great, because simply just like that, imagine that you want to do text classification. Then you simply make an average of all the different words, of all the vector representations of the words, and then your point average will go to the closer to the area of the embedding representation where the meaning, where most of the words of the text lie. So if it is a text about I don't know, rescue by firefighters or something, it will end up the vector sum of all the embeddings will end up close to these words, need and help, because they appear very often. And then you simply make a classification, a linear classifier, a support vector machine, and it can distinguish them relatively well. The thing is that it becomes even better if rather than a support vector machine, you use a neural network, because not only they are more cool, but then you can stack them one after another. And then more of this example. For instance, what are the words that appear closer to the vector representation of frog? And then what you see is that all the closest words are also different species of frog. And funnily enough, one of the vectors is for the Spanish word rana, which I don't know if it exists in English itself, but the embedding even realizes of that relationship, even when it is probably a foreign word. And then other very nice thing is that it is not only, the embedding is not only coding things in the position of the word, but as we were expecting, but we also get a lot of beneficial side effects which are terribly useful. So for instance, not only positions, but also directions in the n-dimensional space represent information. So for instance, here you see this is one of the original embedding papers. They saw very quickly that if you move in a specific direction in the 200-dimensional space, you get to make transformations, consistent transformations in words. Here what they detected is that in this specific dimension, you actually, for all the words, or at least the most common words, which has the more stable and accurate embeddings, you get the equivalent of the word, but in the female sense. This is a very typical example that they do. So you can transform the gender of the word by moving in that dimension. And then what do you do with all these embeddings? Further than simply doing text classification, well, you can do much more, because then it becomes much more doable how to encode a whole piece of text. You simply stack the vector representations of each one of those words in a matrix, and then you can feed that matrix to other algorithms, and it won't be terribly computationally expensive because algorithms are extremely good with matrix operations. And then here I try to represent more or less how this will look like. The first column, for instance, tends to have high values for nouns, and then the last column tends to have high values for things that have to do with health. This is simply a typical example that I use in my work on natural language processing in electronic health records. And then, the top dimension is simply the embedding dimension. In the example, it's only 10 or so, but in reality, it will be 200. And the row dimension is simply how many words you are putting into your neural network, or how many words your text has. Okay, so now I was talking quite generally about how to create the embedding representations of words, but how do we actually do it in detail? So one of the first algorithms, if not the first one on neural networks, was what they call generally they call now skipgram. Also, skipgram was rather the name that Nicolo, I think was the guy, that Nicolo gave to one of the two versions of his algorithm. So what he is doing is simply creating a very simple neural network, the simplest neural network that you can create without transfer function, only one layer, to try to predict from the context words, so these ones are the words around a central word, to try to predict, after a one-layer neural network without transfer function, try to become as close as possible to the word representation of the central word. And he called that CBO, continuous box of words, I think it was. And the other one is the skipgram, which is what people use the most now, which does the opposite. From the central word, with a very simple neural network, you try to predict all the others, all the ones that are in the context, that tend to appear close by. And they are quite relatively equivalent to each other, and I think you get more or less the same type vector representations with similar properties. if they are not mathematically the same, which I wouldn't be surprised of. Okay, and now with a nicer diagram. How does this look like? So imagine that we go again with the dog example, and I think here I am using the skipgram. So yeah, the skipgram. So imagine that we start first. I guess they did this first step simply to keep the old school AI people happy. So we go with the first step of representing the world with a one hot embedding. So you will have a crazy 150,000 dimensional vector, which in reality you don't really use. You rather go directly to this. But for now, 150,000 dimensional vector, where you represent only the central word by putting a 1 on the dimension equivalent to that word, and 0 everywhere else. So, so you will have, in the case of the central word being dog, you will have a 1 in the position, in the dimension that corresponds to dog, and you will have 0 everywhere. Then you have the first layer of the neural network, which is simply a linear transformation of this space into a dense space. This will be what we call the embedding space. And that will be only 100 or 200 dimensional. And what that's going to do is to transform a sparse space to a dense one. This WVD, what it means is that computationally, it is simply a matrix where the first dimension is V, the number of words in the vocabulary. The second dimension, D, is the dimension of the embedding space, which is 200 dimensional in our example. And a matrix is the way of representing when in a neural network, each neuron of the previous layer, so each box is a neuron, connects with every other neuron of the next layer. It is a dense connection. And then later, once you have compressed the information to that latent space, it is another nomenclature they use a lot, you project back to the all sparse space with the transpose of the matrix that you had before. So then every connection in this first layer of the neural network is the same than other specific connection in this other part of the neural network. And then when you have that again in the 150,000 dimensional original space, you apply a softmax. And what is a softmax? Well, a softmax is a funny equation that allows you to do two things. First, you compress every one of these dimensions, so you get these. Do I have like colorful pens? Yeah. So you compress the original space of Rn, so it also, well, Rv, using the nomenclature. You also take it to Rv, but while here, every dimension, what letter am I using? Oh, no letter. Well, every dimension x could have anything value from minus infinity to plus infinity. You reduce this to a representation between 0 and 1. And that's the first thing, which becomes very useful for reasons that you will become aware during the lecture, during the course. And the second thing that it does is that it produces kind of a soft decision between every of those values, all the values that you have here, such that the values that tend to be relatively low, they go all of them to almost 0, and the values that tend to be higher, the highest values, they tend to go to get much higher values in this representation from 0 to 1, such that once you have trained your neural network, you surprisingly get this. For the blue words, that are the ones that tend to appear nearby to dog, you end up getting quite high values, and for everything else, you get something very close to 0. So you have got what, in the average of all your data set, approximates the one hot representation of the words that tend to appear in the context of the word dog, and the same for every other word, not only dog. Yeah. Okay, and why? So what happens about the first two steps? Why are we using the 150-dimensional representation when we were talking before that was terrible? Well, it is because if you multiply, because in a neural network, remember that always when you have all these funny dense connections, what you are doing is simply multiplying these vectors by a big matrix. So when you multiply those vectors by the W matrix, what you are simply doing is selecting in the W matrix the row corresponding to the position where you have a 1. So in reality here, what we are doing is simply, in our training set, is for any word, in the case of the word dog, we are selecting from W the row that was sitting in position number 3. And the same for all the others. For fur, it will be we pick from W the row, the values of the row that corresponds to the position, the second position, and so on for all of them. So the first layer is simply a selector. That's why before I was talking about a single layer neural network, because this is rather the only layer. The first one is only a selector to connect this with the old literature where they were using one-hot representations. And then once you have that embedding, so each layer of this W matrix is a so-called embedding, then you simply multiply by the transverse of the matrix, and then you do the softmax and so on. And here I also have a representation of the softmax. So the whole matrix will be this equation. I am using a bit of a funny nomenclature or a funny way of writing equations, simply to see if it is really of use, because if we use the traditional, the old way of making equations, the traditional way, they are not so good to represent matrix operations. And in neural networks, everything is about matrix operations. So the only thing that I am doing is getting x, which is the original red vector, the one-hot representation, which is a vector of dimension v, 150,000, multiplied by the first by the first dense layer, which is simply W of V rows, D columns. So D is the number of embedding dimensions, multiply again by the transpose, and then apply a softmax. And the softmax, it is applied through the V dimension, so not through the D dimension. And that will result in your Y vector. And the Y vector is this blue vector that is trying to approximate the typical one-hot representation of the typical words that appear in the context of your red word. Then if we transform the softmax by its real equation, you get this thing, and the only thing that it is doing is that you get the exponential of this vector, of the second gray one, and then you divide it by the sum of that thing across all the words. And because of the property of exponential, we get a huge number, a way bigger number, the more the domain, was it domain? Yeah. The domain of the function becomes a bit larger, then it means that this will suppress anything that tends to be low values and make much higher the values that tend to be among the larger values of the space. And then other way of representing it, rather than using my funny nomenclature, is to use this other nomenclature, where we simply focus on two words. The word Y, the blue one, the word X, the red one, and then we divide by all the other ones. And here, this traditional nomenclature, what it allows you to see is that the words that you are going to get in what the neural network is going to end up doing is try to give vector representations to when two words tend to appear in the context of each other. The neural network is going to try to maximize the dot product of those two vectors, which means that when two vectors mean more or less the same, oh man, this is even worse, and I guess these ones are even worse. Oh no. So what that means is that the vector representation of a given word will try to have a high projection with the other words that tend to appear in the context. Well, actually, this, well, yeah, Labrador as well, but if we follow my explanation, this will be, for instance, park. And this, the neural network tries to foster this, so later if we get something very different, like car, so the neural network will try to have the dot product, which is simply the projection, will try for this projection to be very small. So it is this property that the neural network fosters what then gives emergence or fosters all the other nice properties that we talked about before, that similar words tend to appear close to each other in the RD dimensional space, and then certain dimensions in that space, certain directions, tend to represent changes in the meaning of the word and all those nice properties. Let's see, how much am I doing with time? Okay, so we are a bit tight on time. Next time I will be a bit faster. So, and now I will go quickly through some industry applications, although before talk a bit about that. So a typical one that now they are starting to work a bit better is question answering. So Alexa and all those systems, they are able to do question answering on simple situations, especially when you want to buy stuff in Amazon. They are amazing for that, and other things not so much. And yeah, now this is working more or less okay, and before it was simply impossible. You simply feed all this text to a neural network, then you feed this other query, and the neural network tends to be more or less okay on giving an answer. I think that, for instance, for one of the first papers that was doing this quite well was made by someone from this department, Phil Bloomson, which I think is teaching the other NLP course. Other one is answering questions or describing, giving labels to figures. And this shows the flexibility of neural networks. Here you can merge a neural network that has been designed to analyze images with a neural network that has been designed to produce text, which is quite crazy. I mean, before it wouldn't be easy at all, but now it is quite trivial. It is much easier. And then you can create, if you feed it with a lot of pairs of images and the level of the image, it can manage to reproduce that quite well. Not perfect, but relatively well. Other application is lip reading, which some guys since they have been able to do, which could be also extremely useful for blind people, for deaf people, for instance, to be able to enjoy everything that happens in YouTube rather than simply not being able to use YouTube at all. And not only YouTube, but video news, and imagine that in the future we are also able to have glasses. Indeed, I have seen some attempts to this. Glasses that where you are pointing, they read the lips of whoever is talking, and they display what the person is talking. And then these personal assistants that I was talking about before, which are already in the market. Anybody of you with a good phone might be able to use this. Other one that you can look in YouTube and it is already running, which is quite surprising, is that you can get any random video. Well, I don't know if any, but many videos, you can pick them up and tell to YouTube to translate to any language. I chose Korean, but I could have chosen like Zulu, or well, maybe not Zulu, but I could have chosen anything, and I think it works relatively well. Sometimes there are some videos on Japanese that my wife listens, and if I want to see them as well, I put the translator to Spanish or to English. English a bit better, and it was more or less okay. And this is surprising. I didn't think I was going to see this in my lifetime, so it is quite surprising. Okay, so that was for the lecture for now. We are going to have a break of 5 minutes, because otherwise I guess people will hate me. But yeah, later we will continue. Also, in the last slide, you have some papers for reference and some good tutorials, if you don't like reading.